Okay, hello everyone. Let's get started. This is the Foundations of Quantum Mechanics, lecture 12. So today my plan is to discuss Bohm's theory for the many particle case, and then I'll move to a discussion of the so-called Nelson's stochastic quantization, which is quite surprising. And then next time is already the last lecture in the series, and we will talk a little bit about possible extensions of quantum mechanics. But before we get started today, there's a small organizational announcement. So this Wednesday at 6, we will have the tutorial session about the second problem set. I have also put this in the discussion group, and I put the Zoom link right in time on our website before the tutorial session on Wednesday at 6. And then I also am interested in finding out how many people from Erlangen will actually be taking the exam, but I'll also put a question out there on the discussion group. Okay, so let's get started. Last time we were discussing Bohm's theory, and instead of a recap of the single particle case, I'll move right to the many particle case, because that tells us everything, that reminds us of everything. So as we said, Bohm had this idea that you could be talking about trajectories and not come into conflict with quantum mechanics. You could arrange it such that the individual particle would obey an equation of motion, that if you follow this equation of motion and you have the right initial probability distribution of the particle at time 0, then you would be guaranteed that the particle would also have the right quantum mechanical probability distribution at any later time. So in that way, you remain consistent with quantum mechanics, and yet you are talking about trajectories. Now, the question is, how would this be extended from one particle to many particles? And that's actually fairly easy. For many particles, we know that the wave function is a function of multiple coordinates, all the coordinates simultaneously, as shown here. And just as for the single particle case, we can split the wave function into a magnitude and a phase factor. And so this phase that appears in the exponent, of course, this phase is also a function of all the different positions of the particles simultaneously. And now actually the ansatz for the equation of motion for any individual particle is the same as for the single particle case, only now you will be taking the gradient of this phase with respect to this particular particle coordinate that you're looking at, but the phase itself will still be a function of all the particle coordinates simultaneously. So that's the new equation of motion that we will be using for the many particle case, a straightforward extension. And to visualize the situation, we can look at this plot on the left-hand side. When we have, for example, only two particles and they are in one dimension, then we can still easily plot things. So I plot the coordinate of particle 1 on the horizontal axis and the coordinate of particle 2 on the vertical axis. And then, as usual, this bluish shape would represent the probability density. The blue lines represent the wave fronts. That means the lines of constant phase. And the gradient of the phase obviously is perpendicular to those lines. And so if I now imagine a statistical ensemble of different configurations, each of these configurations will be represented by one of these blue points. And I also indicated the direction of motion in this configuration space that this configuration space point will undergo. So again, x1 and x2 are not the coordinates of one particle moving in 2 dimensions, but rather they are the 2 different coordinates of 2 different particles, each of them moving in 1 dimension. So we are here talking about configuration space. But everything else really works like before. And so the same mathematical conclusions hold. So in particular, this consistency with quantum mechanics. So if you make sure that you are starting with a statistical ensemble in configuration space such that the probability density in configuration space, which I again call rho Bohm, is equal to the psi square from quantum mechanics at time 0, then this will also hold for all later times. So the psi, it will evolve according to its Schrödinger equation. From the time evolving psi, we can always extract the phase phi at any given time. And if we then fulfill this equation of motion for each of the particles, we will be guaranteed that the probability density predicted by Bohm will match the quantum mechanical probability density. And so why is this important to treat many particles? Well, for example, we want to be able to treat a system plus a measurement apparatus. We have already seen this is a situation where there will be interactions and the overall wave function is more complicated than just the wave function of a single particle. Now, is this everything? Does everything just work like for a single particle? And the answer is no, not quite. There is one important conceptual difference. Namely, here we already observed that the velocity of particle number j may depend on the positions of all the other particles. And so the question is, how should we interpret this? Is this kind of some influence by the other particles? And the first thing we could check is what happens if I start from something really simple, namely a product state. Product state means the wave function is nominally a function of all the particle coordinates simultaneously, but I can split it, I can factorize it into individual single particle wave functions. And then as a consequence of the wave function being a product, the phase itself will be a sum of individual contributions. The first one only relates to particle 1, the second one only relates to particle 2, and so on. And now something interesting and good happens. If you evaluate the Bohmian equation of motion for particle number j, then you find that, of course, only one of these additive terms will contribute, and that is just phi j, the phase for the single particle wave function of particle number j. And so in this case now, the right-hand side of the equation of motion is really independent of all the other particles, which makes sense because a product state means the particles are uncorrelated, their statistical properties, they are uncorrelated. And so it makes sense that the motion of particle j is not affected by anything happening with the other particles. So that's good. But what happens if we move away from a product state? For example, if we look at an entangled state. So in an entangled state, the psi, the wave function, is no longer a product, so the phase itself is no longer a sum of independent single particle terms. And so then the motion of j really does depend on all the other particle coordinates. And it does so even when there is no interaction. So that's important. If there were interaction, then even classically, of course, we would expect that particle number j feels the other particles. But I can switch off the interaction and still be in an entangled state. The state, of course, has been generated in the past by having some interactions, but now there is the entangled state. I can switch off the interaction and still I got this dependence. And so the immediate question you want to ask is this a sign of non-local influence? Do we get the spooky action at a distance that Einstein was talking about? And the argument is that, well, not so fast. It might be a sign of non-local influence, but it can also be something much more reasonable and harmless. And I first want to discuss the harmless case. So I want to show you an example where this dependence of what one particle does on all the other particle coordinates does not necessarily imply action at a distance. And so I've drawn the simple example here. We are in a state like the one shown here. This is not a product state. You can convince yourself, otherwise this would look different. Again, I draw the wave function in configuration space x1 and x2. And the wave function is composed of two pieces, two wave packets, so to speak. The one wave packet down here. And this is a wave packet that describes a situation where x1 is moving to the right and x2 is moving down. Yeah? Oh, sorry, x2 is moving towards negative values. And likewise, there's another wave function up here, piece of the wave function, that describes a situation where the velocity of particle 2 is positive and the velocity of particle 1 is negative, so just the opposite. And in this situation, we will indeed find that the velocity of particle 2 does depend on the position of particle 1. If particle 1 is more to the right on this axis, then velocity of 2 is negative, otherwise it's positive. So there is a dependence, but this should not be interpreted really as influence of one to the other particle. We rather could tell a very, very simple story, and the story would go like this. We would say, aha, just like in a classical statistical situation where we need probability, we either have a situation where particle 1 is moving to the right, so the velocity is positive, and particle 2 is moving to the left, or another situation where the roles are reversed and the velocity of 1 is negative and the velocity of 2 is positive. So that would sound very familiar to anyone who has no quantum mechanics background. And so we do have correlations, but there's not really any influence as such. Okay, so that sounds harmless. The question is, can we always cook up such a story that we discuss away what seems like an influence? And then the answer is no. But in order to test this, we really want more. We want something with control. We want to check whether we can do something to particle 1 that will influence the trajectory of particle 2. If we can show this, and this happens even over distance without any interactions, then indeed there will be non-local influence. So we have to control something. And so that means we would like to prove the non-local influence by showing that a force on particle 1 can change the trajectory of particle 2, even if they are far apart. So the situation would look like the one shown here. If I plot only the position of particle 2 as a function of time, but there's a certain point in time where I decide whether or not I apply a force on particle 1. And then if the situation is like the one shown here, that with the force on particle 1, x2 deviates in its trajectory from what would happen without the force on particle 1, then I can really rightfully claim that I can control particle 2 via a force on particle 1, even if there is no other interaction. And that is a really spooky action at a distance. Okay, so the question is, can I set up a situation like this? So my goal would be to find a wave function and also some force that I apply, and to show that indeed the Bohmian trajectories will change for particle 2 depending on what you do with particle 1. Okay, so here's a wave function that I've constructed for you that will be the starting point for doing this. It again consists of two pieces. So there are two wave packets again. One wave packet here is the one where the position of particle 1 is large and particle 2 has a positive velocity moving upwards in this plot. And then there is the other wave package that describes scenarios where particle 1 is at a negative position around -a in this plot, and the velocity of particle 2 is negative. So the velocity of particle 2 is kind of correlated with the position of particle 1. I can easily construct this. I have written down the wave function for you just to inspect, but there's nothing very special here. Phi would be a Gaussian wave packet, for example. Okay, so now I'm going to apply a force, and there would be many ways to do this, but the force that I want to apply is actually one that depends on the position x1. So I want to push these wave packets towards each other. This is what I want to achieve. And then when they are overlapping, they will show an interference pattern, and it will be this interference pattern that helps me to prove that the trajectories of particle 2 are really changed. How do I push them towards each other? I cannot simply apply a homogeneous force that is the same everywhere in space, because then I would move both of the wave packets in the same direction. So what I will do instead, I apply an inhomogeneous force that is different at different points in space. In other words, I can also say I apply a potential that is not just a linear potential. And so the potential that I will apply now is a harmonic potential. because it's the simplest choice, not very important, but still. So what happens if you have these two wave packets? Here I'm showing only the coordinate of particle 1. You have these two wave packets at the two different positions, A and minus A. And now you apply a harmonic potential. Well, the wave packet on the right will experience a force to the left. The wave packet on the left will experience a force to the right. So this is exactly what I wanted. Yeah? And what happens over time, if I now wait a little bit of time, is that these two wave packets are really pushed towards the center, where they will overlap. And if you are now very careful, you can even understand exactly how these interference fringes will look like. You just have to look at the velocities of the different components, both in x1 and x2. The velocities are connected to the momenta. And if you superimpose basically two plane waves with equal and opposite momenta, this is the kind of interference fringes that you will get. Okay, so just believe me for a moment, these will be the interference fringes that show up. What does this mean for the trajectories? That's the question, for the Bohmian trajectories. And well, it turns out the Bohmian trajectories in this original situation, they are very simple. So x1 actually doesn't change and x2 just moves either down or up, depending on which wave packet it is in, and it moves at constant speed. So it's very, very simple. In this situation, the trajectories are much more complicated. In particular, at the specific point in time that I'm showing, where the wave packets are overlapping perfectly and I get a perfect standing wave, then I can have a situation where the wave function is purely real, like cosine kx. And in that case, I don't even have a phase gradient. And then at this point in time, actually, the particles might stand still. And at other points in time, they will do a relatively complicated dance in this evolving interference pattern. So I have now plotted for you these trajectories of particle 2. We want to compare the two situations. Either I don't apply a force on particle 1 or I do apply a force on particle 1. And I've plotted for you, so to speak, the space-time plot of the trajectories of particle 2. Let's first look on the left side where there is no force acting on x1. This is the situation with the two wave packets. And I said the trajectories are very simple. Either there's a bunch of trajectories that belong to one of the wave packets that are just moving to the right. And there's another bunch of trajectories that belong to configurations sitting in the other wave packet that are moving to the left. And it's just linear motion, very simple. Again, this is an ensemble picture. So to speak, the idea is in any particular experiment, only one of these trajectories would be realized. But now I repeat the same experiment with the same wave function again and again. And I look at the Bohmian trajectories, which are stochastic because the initial conditions are stochastic. And then I would get this picture if I plot all of these trajectories. Okay. And now if I do apply a force on particle 1 and I get this funny interference in the wave packet and configuration space, and I get the Bohmian trajectories for particle 2, this is what I get. So I see rather complicated dynamics. They are wiggling around. They may even change direction. So definitely they are different. And so I can clearly distinguish the two situations. If I did apply a force on particle 1, the trajectories of particle 2 will have changed. And this cannot be discussed away anymore. So we can really exert a non-local influence over trajectories in this way. Okay. And now Bell would say, well, I told you so. This has to be so. Why? Because Bohm's theory is obviously a hidden variable theory. It talks about the particle positions that are not part of the usual quantum mechanics. So these are additional hidden variables that I cannot access easily, but I am still willing to talk about them, and I'm willing to talk about the trajectories. And as we showed, it makes predictions, at least for the probability density of the particle positions, that are completely consistent with quantum mechanics. So according to Bell, this must be a non-local theory, otherwise it couldn't be consistent with quantum mechanics. And so that was what was to be expected. This is the idea. I will pause here for a moment just to make sure that this example was understood, or maybe there are already some questions. Okay, I don't see any questions at the moment, so I will just move on. One of the questions you can have is, does this funny effect, this non-local influence, then does it mean faster than light signaling? And the very important answer is no. Okay, but before I go on, there's a question. Isn't I move back one slide. Isn't x1, let's say, the position of a sort of center of mass of psi1 squared, or really the position of the particle? No. So x1 and x2 are really the positions of the particles. I'm here working in the configuration space. That is the space where I plot simultaneously the coordinates of both particles. And I have a wave function in configuration space. This is what I'm doing here. And when I talk about x1 and x2, I'm not talking only about some center of mass of the wave packets or so, but I say that, say, my configuration is precisely at this point, which means particle 1 is, let's say, slightly to the right of plus a, and particle 2 is at whatever it is, it has as position. Yeah. So I'm really talking about configuration space. Oh, could you elaborate again? That's a good question. A bit why entangled particles cannot be thought of as interacting particles. That's an interesting question. If I look at these trajectories qualitatively, of course, I could start making a story about, aha, entanglement means some kind of interaction. And indeed, in Bohmian's theory, if I could say, aha, there's an extra force coming from the other particle, so let me call that an interaction. But what we mean here by interaction is really just the normal way of talking about interaction. So if in my Hamiltonian I have a Coulomb force or some other kind of force, then I say there's an interaction between the particles. If they are far enough apart, or simply they are not charged or something, so they don't interact, then I will say there is no interaction. Now, if I then find such funny effects like the one shown here, these effects can happen even over very long distances. So you would not want to just simply say, oh, these are interactions. In any case, these interactions would be traveling faster than light. So this presents a conceptual problem. Even if you wanted to try to say, I have discovered a new form of interaction magically by entanglement, then it would still be faster than light and create all kinds of problems. Yeah, in Bohm's theory, we really talk about position and velocity of a point-like particle. Yes. And also in the free particle description. Well, in all, so is your emphasis on the point-like particle? So yes, so the answer is yes. We talk about position and velocity of a point-like particle. And yes, the speed is the same kind that we are also discussing now. So the gradient of the phase, that's the velocity. So yeah. So this is basically the idea. Okay, maybe I move on a little bit. I still wanted to make a very important remark. This might sound at first sight as if we had faster than light signaling, but the answer is no. The point is, we cannot actually observe these trajectories. They are hidden. They are, so to speak, the trajectories of hidden variables. What we can observe reproducibly in an experiment is only the statistics of the particle position at some particular time, say coordinate x2 at some time. And if we look at this statistics, I can do the following. I can take the joint statistics of x1 and x2. According to Bohm, this is psi of x1, x2 squared. And then I say I'm not interested in particle x1, so I integrate over that coordinate. And what I'm left with is the probability density for particle 2, okay? And now one can easily show, I will not do it here, that this probability density that you can really observe in repeated experiments is really independent of any force you apply to x1 if there are no actual physical interactions. And so regardless of what you do, you will find always that this probability density of particle 2 remains unchanged, regardless of what you do on particle 1. You would have to do something with particle 2, then of course you can change it, but anything that you do with particle 1 will not change this probability density. And so that means there is no faster than light signaling. You see an effect in the trajectories, but you don't see an effect in the statistics at any given time of, say, the position of particle 2. So if you make a cut at any particular time and you record the positions of all the particles at this particular time and you plot the probability density, it will look exactly the same with the force as it does without the force. No difference. And so you wouldn't be able to, by just looking at particle 2, to know that something has happened to particle 1. Okay. I have some further notes on Bohm's theory, but this was already the most important pieces. So we know the equation of motion, it's consistent with quantum mechanics, but if you go to many particles, it turns out to be non-local, and it has to be non-local. People ask, for example, what about spin? Can you introduce spin? And the answer is yes. So if we deal with spin, let's say for a single particle, then this wave function gets actually multiple components. So there will be a wave function for the spin up part and a wave function for the spin down part. And so sigma here, in this case of a spin 1/2 particle, would be either up or down, so an index. And what you can do then is you define the total density by summing over both spin directions. And you can also define the total probability current density. And if you do this, then you will find that both together, of course, fulfill the conservation of probabilities. So this continuity equation is fulfilled. And then if you use this ansatz here for the velocity field, you will find that the particles behave just in the way that you would hope them to behave. And again, you will be consistent with quantum mechanics. People do explore relativistic extensions, but there are some issues, and we will come back to that a little bit later, so it's not so easy. And the last thing that I want to highlight is Bohm's construction is really not unique. So once you know the idea of Bohm, that you somehow set up a velocity field that will take the particle trajectories to where they should go in order to always match the quantum mechanical probability density. Once you have understood this concept, you could think, oh, is Bohm's theory the only theory that does it right? And you will figure out very quickly that no, in fact, there are infinitely many choices of the velocity field of the equation of motion that will still remain consistent with quantum mechanics. And the idea simply is this: in the end, you look at this continuity equation and you want that the evolution of the Bohmian probability density follows exactly the evolution of the quantum mechanical probability density, which means effectively that the divergence of the Bohmian current density and of the quantum mechanical current density should be the same. So what you want to achieve is that the divergence of rho, where rho is the Bohmian rho, put a little b, rho times v, that the divergence of this equals the divergence of the quantum mechanical probability density, probability current density. But the funny thing is, there are many, many choices of v that will make the divergences match, because there's an ambiguity, you know, if you have two vector fields that have the same divergence. And this alone would be sufficient to match the quantum mechanical predictions. And just to give an example here, if you consider the hydrogen atom, we were a little bit disappointed that Bohm predicts that the particle is just sitting stationary at some place and doesn't really move because there is no gradient of the phase, so the velocity is 0. However, you can easily set up a velocity field like the one shown here, where the particles keep moving around in circles around the origin. And this, of course, doesn't change the probability density, so you can keep the probability density constant, and it can still match the quantum mechanical probability density all the time. And so this would also be a valid ansatz for trajectories of particles that have just the right quantum mechanical probability density. So it's not unique. And that, of course, was also a criticism. Would have been more powerful, of course, if it were unique, because then somehow maybe you are on the right track, but here there are many possibilities. Okay, any questions still on Bohm? We will be finishing Bohm and moving to Nelson. Okay, I don't see any at the moment, so I will move on. Nelson's theory is also a theory that talks about trajectories. In that sense, it's conceptually very similar to Bohm. If you look at the trajectories, we will find that whereas Bohm's trajectories are very smooth, Nelson's trajectories are actually something like a random walk, together with some drift superimposed on it. So if you were to show me these two kinds of trajectories and ask me, okay, if you had to guess which one might be a more realistic description of what goes on microscopically with an electron, I myself might opt for Nelson's theory. But of course, that's a matter of taste. These are hidden variables, so we can't observe them. Nelson's theory is called stochastic quantization, and you will see why when we arrive at the point, but I want to keep open the surprise, so to speak. Okay. Now, in order to discuss these funny random trajectories, we have to discuss a little bit stochastic processes that's needed here. And they are, of course, very important in many fields of physics, also completely outside quantum mechanics in particular, Brownian motion of particles in a gas or a fluid. So the typical situation is shown here. You have the position x of a particle as it evolves in time t, and it executes this very jittery random walk. Maybe there's a drift, which means it is pulled towards some region in space in addition to having the random walk. But in any case, so the random walk itself is the simplest stochastic process, the one that everyone starts with. And it just says, if I want to know the position at time t plus delta t, I take the old position plus I add a random step. And this random step in the simplest version is independent of my current position. And it's a random variable, and you can characterize it by its variance. And if you want to have a nice continuum limit where the time step can be sent to 0 and you get consistent results, then it turns out that the variance of this delta x, about the variance of the random step, should scale linearly with delta t. Everything else will lead to problems, okay? And so the prefactor, the constant prefactor, we traditionally call the diffusion constant, or 2 times the diffusion constant. Okay, so that's a random walk. Now, one thing we will be interested in the story is, can we talk about things such as, for example, the instantaneous velocity or instantaneous acceleration of a random walk? And there you run immediately into a problem if you are not careful. So we could define in the usual way that we take derivatives. We could just take the difference of positions and divide by the time interval, and then later we would let delta t go to 0. So in our random walk, this difference in positions is just the random step delta x, and so I divide this by delta t. And then, since I know delta x is randomly fluctuating, I better have a look at the variance of the whole expression. And so if I work this out, you know, the variance of delta x divided by delta t, what is this? Delta t in the denominator is just a number. I can pull it out of the variance, but I have to remember the variance takes the square of the random variable. So it really appears as a square in front. And then variance of delta x, well, we just said this is 2d times delta t. And so what I see very quickly is that the variance of this expression that seems like the instantaneous velocity, that this variance goes like 1 over delta t. And now that's very dangerous, because if I send the delta t to 0, I get infinity. And this is really what really happens. So if I plot this instantaneous velocity in the limit where delta t is very small, or I'm eventually sending it to 0, what I get is known as white noise. So it's, so to speak, very rapid fluctuations, very infinitely large variance. And the proper way to deal with those is then to, for example, calculate correlation functions. So what's the correlator between this velocity at time t and time 0? And what you would find is that this correlation function is actually a delta function. So if t is non-zero, then it's 0, they are uncorrelated. But if t is 0, then it's infinite, because that's the delta function at 0 argument. Okay, so that's a well-known problem. That's why people usually do not talk about velocities of random walks. Okay, so moving on, I want to extend the random walk a little bit, just a little bit, by introducing drift. So we had the first part of the equation that was the random walk. And now I want to introduce extra drift. That means there's an extra velocity field that may depend on position. So the position appears as an argument. And that tells me that superimposed on this random motion, there's a systematic drift, superimposed on top of it. And I will show you one famous example. If we assume the simplest possible dependence of this drift velocity on the coordinate, that might be a linear dependence. So I could say this drift velocity always points back towards the origin. So that's minus some prefactor times x. It always points back to the origin. So if I'm at positive x, I will go to smaller x. If I'm at negative x, I will go to more positive x. And so if I plot this x versus t, this is what it looks like. It has a typical time scale. It's actually given by 1 over gamma, this prefactor. And otherwise, it always stays in a certain range of values. And if you calculate the probability density of the position x, if you run this process for an infinitely long time and keep track of where the x is at any point in time, and you eventually accumulate a probability density, this happens to be Gaussian. So it's very simple, a Gaussian probability density. And this whole thing is sufficiently important that it has a name. It's called Ornstein-Uhlenbeck process. But okay. So that's a version, a kind of modification of a random walk with this extra drift term. Fine. And this is what happens, for example, in some physical systems. If you're in thermal equilibrium and you have an overdamped particle and it experiences some thermal forces, this is what happens. Okay. So just quick aside, that was an example, but quick aside, what about the probability density itself? What we can write down is an equation of motion for the probability density. So the time derivative of rho, what is it? It has actually two terms. Both can be written, by the way, as the divergence of some probability current density, because it always must be like this. But it has two pieces, one related to the drift. So that's just rho times v. That's the current density for the drift. And then there is another term for the diffusion. There the current density goes like the gradient of the density. And then if you take the divergence again, what you get is a second derivative. And that is actually what you expect for a diffusion equation. So it makes a lot of sense. So this is how the probability density evolves in time. If we, for example, we could start in a situation where rho is very concentrated at some point in space. And then as we wait in time, it might actually, well, first it might drift to some direction, depending on the drift term, but it also will spread, that's the diffusion term, and so it will become broader. So this is what happens in time with our density. Okay. And now the funny thing is you can ask, okay, but let's suppose I run this for a very long time. Maybe the density will settle into some stationary pattern and not change anymore. How does it look like then? So you would want to set d rho over dt to 0. And to make the situation easier, I will now assume that the velocity can be written as the gradient or minus the gradient of a function. This is actually the situation if you have an overdamped particle moving in a potential u, then the force is minus gradient of u, and mu would be some kind of mobility that tells me how quick is the particle given a certain force. Okay, if you have this situation, you can easily solve the equation that when you set d rho over dt equals 0, and the solution should almost look familiar. The solution can be written as an exponential, and the exponent there is minus the potential, and then there's a prefactor, which is the ratio of mu and d, the mobility and the diffusion constant. And it turns out that's a result due to Einstein from more than 100 years ago. In thermal equilibrium, the diffusion constant and the mobility are related by the temperature, essentially. And if you insert this, then you come back to a very well-known result, then the density is just the Boltzmann distribution. Yeah? So you see how these drift diffusion processes can also eventually give you thermal equilibrium. That's just one example of their application. Okay, so but this is just for background, keep this in mind. And now we want to do something more advanced. This is where the story becomes really interesting and more mathematical. Mr. Nelson was a mathematician. We now want to come back to this question that I raised in the beginning. Okay, what about the velocity at any given point in time, the velocity of this random walk? And we found, oh, it's really bad. It's fluctuating infinitely. We cannot even define it properly. So we gave up. But it turns out we do not need to give up. We can do this more systematically. We can talk about somehow average velocities. And it will be crucial how we average. And we will average in a way where we say, I do not just take an average over all possible trajectories. I take a conditional average, conditioned on some, well, constraint. For example, I want to know that my trajectory passes through a certain point, and based on this constraint, I want to evaluate expectation values. So let's talk a bit about conditional expectation values. So let's say I have some arbitrary random variable x. I have another random variable that I call y, which may be correlated with x, okay? And now I want to evaluate the expectation value of x, but not just so, but with the extra constraint that y takes on a given value, which I here called y0, okay? And the definition of this conditional expectation value is very simple. You take x, and however you multiply it with a delta function that sets y equals to y0. You take the expectation value of this, so this and the expectation value, that's the same thing for me. And then for normalization, you still need to divide. You divide just by the expectation value of the delta function itself, which, by the way, is just the probability to find this value, y0. Okay, so this is the expectation, the conditional expectation value. And we can now apply it to our particular situation, to the random processes. For example, let us ask about this random step delta x at time t. And let me take the conditional expectation value given that I know that at time t, I was at coordinate x. And if you go through the different steps, you quickly realize the result is 0. And it's simply 0 because by assumption, we said that the random step delta x is independent of the current position. So the next step you do is independent of where you are currently. That was our assumption actually in defining the random walk. Okay. So, and then delta x, it had no bias because it also, any bias would be part of the drift term. So it was equally likely to go plus or negative. And for that reason, the expectation value is 0. Okay, fine. Now we will do something quite interesting. We will just say, oh, again, let me look at what is the expectation value of this random step delta x. But instead of setting the value of my position at the beginning of the time step, I will now set as a constraint the position at the end of the time step, t plus delta t, okay? Now you go through the same calculation, but you do not find 0 anymore. It's not very difficult calculation. You just need to be a little bit careful expanding some of the delta functions. What you find is this, at first sight, rather complicated looking expression involving the diffusion constant, the time step, and in particular, the derivative of the probability density. In any case, it's not 0. And so that's maybe a little bit surprising at first, but it makes a whole lot of sense if you think about it. So here I plotted the situation, I plotted the probability density rho, and I claim that we are currently somewhere here. So that is the position on which we condition our expectation value. I called it x plus. And the question we are now asking is, okay, if I know that at the end of the time step, I'm here at x plus, what was the random step that took me here? And it turns out the answer is, well, since the probability density is higher to your left, obviously, than to your right, it's just more likely that you came from the left if you ended up here. If you came from the left and you ended up here, then delta x must have been positive, obviously. So most likely we arrived at this x plus coming from the left, where rho is larger, so there's more likelihood to come from there. And that means delta x must actually be positive on average to arrive at this point. So this is kind of the reasoning. If you condition on something else, like the position at the end of the time interval, you may get different answers. Okay, so good, fine. This is nice. What does it mean in practice? Well, let's come back to this kind of instantaneous velocity that we wanted to have in the beginning, and then we found out, oh, the variance is infinite, too bad. But now we want to talk about averages. But we can't just take the average of the velocity overall trajectories. That would be too boring. We want to condition it on the position that we are currently at. And then we already understood now there are these two ways of doing the conditioning. Either we condition on the position at the beginning of the time step or at the end of the time step. So what's the expression for this kind of instantaneous velocity? Well, we would do the usual difference quotient. So x of t plus delta t minus x of t divided by delta t. Later we can let delta t going to 0. And now we condition on the beginning of the time step and take the conditional expectation value. If you go through the math, you find, well, I just find the drift velocity. That makes a lot of sense. The random step averages out, and what you're left with is just the drift velocity. Okay, fine. But now we do the opposite. Now we say, well, let me just take the same expression, exactly the same expression. This is exactly the same expression. But let me take the expectation value conditioned now that I know the end of the time step, not the beginning, but the position at the end of the time step. If I then go through the math, I will get this extra term that I just discussed. And overall, if I'm in the stationary limit already, so rho is not arbitrary, then I find I get minus the drift velocity. So this sounds very, very odd, but it turns out this is also physically makes a lot of sense. So again, here is the plot of x versus t, a typical random trajectory. I want to keep this particular point fixed. And then I can ask two questions. I can ask, well, if this point is the start of the time step, I can ask where on average will we go from here? And the answer will be, well, you will go in the direction of the drift velocity. And let's say if we are in this Ornstein-Uhlenbeck process, I will go to smaller x. I will be pulled back to the origin. So if I start at this point, in the future, I might likely go back to the origin. Okay, fine. But now I ask the second sort of question. I say if this point is fixed, but this point is actually the end of the time step, I ask the question, how did I arrive here at this point? And the answer is again, well, you likely arrived from smaller x because there's more probability density. You probably came from smaller x, and this was just a random fluctuation towards larger values of x. And so the velocity in the backward direction, so to speak, where you ask, where do I come from, is just the opposite of the velocity in the forward direction. So instead of v, I get minus v. So if v is negative in this picture, then minus v is positive. So that's the situation. Yeah? Is this at least plausible? I mean, you have to believe me that the math turns out like this, but you understand it depends very much how precisely you ask the question. And I claim that these mathematical answers, they do actually make sense. Okay. So at least you're learning something about stochastic processes, probably more than you learn in your statistical physics classes. That's already a good thing. Now we want, now we can generalize this slightly. Yeah. Let me assume I'm not just interested in the position x, but maybe an arbitrary function of x. Some function of x of t and maybe even of t. And I want to say, aha, this looked like taking a time derivative, but apparently there are two ways of doing it, and I will distinguish them. I will first introduce what we could call the forward time derivative. And what do we do? Well, we keep the current position fixed at the start of the time interval, and then we take the usual difference quotient, so f at the end of the time interval minus f at the beginning, divided by delta t, and I let delta t go to 0, of course, and I take this conditional expectation value. Okay, fine. And then we just learned there is an important distinction. We can also do the opposite. We could say, what I keep fixed is the position at the end of the time interval. You look here, the beginning of the time interval, I now decided to shift to t minus delta t. And so what I keep fixed is the end of the time interval. And then again, I take the difference of f values and divide by delta t and let delta t go to 0. So that is the two situations that we discussed here. Either I'm going forward one step in time, or I'm asking, where did I come from? Okay. Okay. And now this is only slightly more general. One can go through the math, and one finds indeed that for such a drift diffusion process, not for an arbitrary stochastic process, which could be even more complicated, but for this kind that we are discussing, one finds very compact formulas. So the forward derivative of an arbitrary function f of the coordinate can be written in this fashion. It may depend on the explicit time dependence of f. That's trivial. That has nothing to do with a random process. It depends on how the drift will change the value of f, simply because the x argument of f is drifting. And then there will be an extra term due to the diffusion. Okay. And likewise, the backward time derivative, and it turns out that this backward time derivative has two crucial differences in signs. Okay, fine. So that's good. That's a good starting point. We can now apply it quickly without going through all the extra math. And one very nice and important thing is here, the result of doing this can still, again, be understood as a random process, because the result is still a function of x of t, and x of t itself is still the same old random process. So I can not only do this once, but I can do it several times. I can take these forward and backward time derivatives of some arbitrary function of the position of a random process. And yeah, I can apply it multiple times. And since we are dealing with these conditional expectation values, even though we have this heavily fluctuating random process, we will get finite reasonable results. Okay. And now comes the big step. I just said, okay, you can take these time derivatives not only once, but twice. What does it mean to take a time derivative twice? Well, that's calculating an acceleration, right? So taking it once is the velocity, taking it twice is an acceleration. So what happens? Can we define the acceleration of a drift diffusion process? And maybe some very rough picture would be, yeah, I'm at this point up here. The acceleration should be something like the curvature of the trajectory. Maybe it's downward curved. It's hard to tell, you know, it has these wild fluctuations. If I do it in a naive way, my answer will be infinity or even ill-defined. But what Nelson did is, he said, look, by these conditional expectation values, I can define a reasonable acceleration. And now there are still many choices because there's the forward and backward derivatives. And what he proposed is this most symmetric of all choices, where you take the forward and backward derivatives and you take them even in the two different orders, which matters. And that's what you define as your acceleration. Now, if you do this and you apply the formulas that we just learned, you can quickly convince yourself that the acceleration, which still is a function of x, which is a random process, that this acceleration can be written in terms of the velocity field, of the drift velocity field. So, okay, v times the derivative of v, and then this second derivative of v. And just as a quick example, we could take the Ornstein-Uhlenbeck process. You remember the drift there is linear in x. And if I go through this little math, I will find an acceleration that is minus gamma squared times x. So it kind of makes sense. It's really curved towards the origin. That's where the process always wants to go back to. It is not implausible that this might be a reasonable acceleration for this kind of process. Okay, so that's the acceleration of a drift diffusion process. What do we do with it? Well, what do we do with accelerations in physics? In physics, we need the acceleration, for example, in Newton's equation of motion. We say, aha, if you tell me the force and the mass, I tell you the acceleration. It's just F divided by m. And by knowing the acceleration, I know how the particle moves and so on, and I can calculate the trajectory. Now let's be ambitious. Let's say, aha, give me a give me a force field, and I will try to produce for you a drift diffusion process that has the acceleration that you would expect from Newton, so F over m. Let's try this, whether this leads to interesting diffusion processes. Okay, so the goal is to find a process with a prescribed acceleration. This acceleration is not arbitrary, but it's just a force divided by some mass. So I'm now thinking in terms of one particle. It has a mass and undergoes this drift diffusion process. There is also some force field that someone told me about. And to make it even simpler, I will assume this force derives from potential. So it's minus the gradient of a potential. Okay, so just like Newton. The question is, can we find a drift diffusion stochastic process where the acceleration would be F divided by m in this manner? Okay, so I can now plug in my newly found formula for the acceleration of such a stationary process and thereby get an equation that will tell me what is the drift velocity field that I would need to make this true. So it's a differential equation for v, and I would still have to solve this differential equation for my drift field. Now, you see that all terms in this equation are derivatives. So what I can do is actually, or I can rewrite it as all terms being derivatives, because the first term is actually the derivative of v squared if I put a half in front, because otherwise it doesn't work. Okay, so all terms are derivatives on the left and right hand side of this equation. So I can take an integration once over x. And then what I get here is a simpler equation where I have v squared, I have somehow the derivative of v, and I have the potential itself instead of the gradient of the potential. And now I have, of course, some integration constant. Okay, fine. And now I could try to solve this equation somehow. but I can also rewrite it in terms of the density itself, because if we are interested in a stationary process, then we saw before that there's a direct relation between the drift velocity field and the stationary density. I think I didn't explicitly show this equation, but this is what happens when you look for the stationary solution here. Okay. So, sorry. So what we can try to do is rewrite this equation for V in terms of rho. Okay. And what you would get if you do this, inserting this relation between V and rho, is a relatively complicated looking equation, and you wouldn't really make sense of it. So it's too complicated, so you don't recognize it. But now I say, well, rho is a positive number, so I can also write it as the square of another number, a square of another field that can be both positive and negative. Which name should I give to this other field? Well, let us call this psi. And let us just say, let me define rho equals psi squared. So this is an equation that basically defines psi. And it will always work because rho is non-negative, so no problem. Now, then I can insert V into the equation. It's now logarithmic derivative of psi, basically. I go a few steps, and what I see is a very interesting looking equation. Second derivative of psi, u times psi, and some constant times psi. And now you should recognize this equation. Because, well, especially if we choose this letter, this is nothing but the Schrödinger equation. In order to bring it exactly to the form of the Schrödinger equation, I just have to choose a certain value of d, or you could also say I define my h bar in this formula. So I set d equals h bar divided by 2m. I inserted it, and I get exactly the stationary Schrödinger equation, where I interpret the constant as being the energy. And so this is the reason why this procedure is called stochastic quantization, because we started from a discussion of stochastic processes and we ended up with a Schrödinger equation. And at least I found it amazing the first time I saw it. So just to summarize really the concept, once we understood how you could define in a reasonable way the acceleration of a random process, we said, let us find any drift diffusion process where this acceleration field is given by some force field or the gradient of some potential. And then also we set the diffusion constant equals to h bar over 2m. That just fixes the numbers, so to speak. And what we found is, for any such drift diffusion process, if we define a new function psi equals the square root of rho, then this psi will actually be an energy eigenstate of the stationary Schrödinger equation for this very same potential u of x. And that was the important insight of Nelson in 1966. You start with demanding something of the stochastic drift diffusion processes, which looks very much like Newton's equation, but now applied to this more complicated definition of an acceleration that you need for the stochastic processes. And you end up with probability densities that are exactly the probability densities of the energy eigenstates. And I must say, I at least know of no other example where you end up deriving the Schrödinger equation in a way where it is not at all obvious that you somehow cheated and brought in some features. Of course, if you know what you want, you can always sneak in something at the beginning, but here it's not obvious at all that you did this. How is the, okay, there's a good question. How is the phase of the wave function defined in this derivation? Well, the point is here we are at the moment only talking about the stationary Schrödinger equation, and at least if I don't have a magnetic field, then I can always find real valued wave functions for the energy eigenstates. And so that's the reason also why I took this psi squared instead of magnitude of psi squared. So at the moment, the answer is there is no phase field. We will a little bit later come back to reintroducing the phase field when we look at the time-dependent Schrödinger equation, where it absolutely will appear, and then the phase field comes back. But right now, it's just eigenstates, stationary eigenstates. And as long as you don't have a magnetic field, you don't need any phase field. But good question, of course. That doesn't mean that you don't get any interference phenomena. For example, if you have a particle in a box, you get standing waves, and this is also already some kind of interference phenomenon. It's just not time dependent. Okay, so I hope you are sufficiently impressed. I now want to discuss some examples. The first example is exactly when we have a constant potential. Let's not be ambitious and let's not start complicated. Just a constant potential. It could be an infinitely extended, I mean, just a free particle like this, or maybe it could be an infinite potential well like this, where inside the well you have a constant potential and outside it's zero anyway. Okay, so anyway, a constant potential. It turns out, of course, we know from quantum mechanics, the solutions are, well, at least if you think of the particle in a box, the solutions are standing waves, right? And this would be the density of these standing waves. So if the density corresponds to this sine squared, basically, then it looks like the one shown here. And you can immediately figure out what is the drift velocity that must correspond to this density. Once we know the density, we don't need to go through any complicated thing anymore. Once you tell me the density that results in the stationary state for a drift diffusion process, I can immediately tell you what is the velocity. So that comes simply by solving the stationary equation where d rho over dt equals 0, and then this follows. Now, if v is the logarithmic derivative of rho, and you just go through the math, you find that v looks like shown here. So it's very funny. At the points where we have perfect destructive interference and the particle should never reach those points, the velocity field becomes infinite. So meaning the particle, the drift diffusion process is pushed away very strongly from these points. And then somewhere in the middle, of course, the velocity goes to 0, so there's no drift. And then if I go closer to the other, to the next 0, I get a negative velocity, meaning my particle will be pushed back to the other side. So either this side or this side. Now, what does this mean for the random trajectories? Just a moment. For the random trajectories, what it means is if I start with my particle inside one of these regions between two interference zeros, then it will forever remain in this region and then execute some kind of drift diffusion process there. Okay, so there's a question. So you claim we have no trajectories a la Bohm. Well, I would say we still have trajectories, only they are not a la Bohm, but they are these stochastic trajectories. Oh, and your question is it possible to find a deterministic fundamental model from which such stochastic behavior emerges? Well, if you insist on it, it's not very difficult to construct, say, chaotic systems whose dynamics would give you basically, if you coarse grain it in time, will give you white noise, and then this white noise could be used to drive your particle that you're interested in, and then it would give rise to such a random walk. But there are infinitely many possibilities. So if you have then made up one such model, you don't know whether it has anything deep to say about reality. So it's rather easy to generate at least approximations of noisy processes from purely deterministic dynamics. You just need a chaotic system. There is another question. What about Bell? I guess So is it the question about non-locality? Then the answer is simply that just like Bohm, Nelson's theory is also a non-local theory. I mean, we cannot see it right here for the stationary case, because then we cannot apply a force and control the other particle. But we will in a moment say something about the time-dependent case, and the situation is of course exactly the same as for Bohm, because this is a theory that is consistent with quantum mechanics, so it has to be non-local. Okay. So if there's no follow-up question, let's move to the only other example I have prepared, which is the hydrogen ground state. There we know the wave function is basically an exponential decaying outward from the origin. And I can, again, easily calculate the drift velocity, again, the logarithmic derivative, or gradient in this case. And it would just be a drift velocity that is always pointing inwards towards the origin, towards the nucleus. And then you would see trajectories like the one shown here. So it's very pleasing in a way. To me, it looks like it could be a realistic model of what the electron does. But of course, you cannot tell, yeah, because it's fundamentally a hidden trajectory. Now coming back to some of the questions, actually. The first question, well, it doesn't yet answer how deterministic dynamics could produce this random walk, but it answers, it's still an interesting observation. So we had said, well, just to make this match with the Schrödinger equation, I need a particular form of the diffusion constant. I need to say, let me just assume or postulate that d equals h bar over 2m. Or you could also put it the other way around. You say, if I know d and m, then this tells me what is h bar. Okay. So anyway, if we take this serious, the diffusion process with this diffusion constant, how could we possibly interpret it? And it turns out it's very interesting. This would result if you had a diffusion process made up of elementary random steps, where each random step is actually proceeding at the speed of light. So at the speed of light, you are moving in some random direction. Here I put it in one dimension, but you can do the same in higher dimensions. So c times delta t, but plus or minus, that's the random step. And this will work and give you the right diffusion constant if you pick a certain value for delta t. And this delta t, you can work it out, would be h bar divided by mc squared. But what is this? This is a well-known time. It's the Compton time, so the inverse of the Compton frequency for the electron. So for example, 10 to the minus 21 seconds for the electron. So it's a time that comes up in relativistic quantum dynamics. It's also related to this Zitterbewegung in relativistic in the Dirac equation. And so this would give rise to the correct diffusion constant. Now, no one knows whether this tells us something deep or not, but it's an interesting observation. So that's the first thing. This diffusion constant seems to make some physical sense. And then there was the other question that you guys had. What about the phase? And then also what about the time-dependent case? And it turns out they are related. So in the time-dependent case, we have to slightly extend the equation of motion. You know, there is this random step, delta x, and then there's the drift. And we know that if we are in the time independent in the stationary case, then I can immediately write the drift velocity in terms of the density rho itself. So that's what I've done here. However, if I'm in a time dependent case, that is not guaranteed. So there could be an extra deviation from that. And so I must postulate that the drift velocity is maybe more complicated and there could be an extra term. And the only ansatz that Nelson makes and gets away with is that this extra term for the drift velocity has the shape of a gradient. Yeah, so the gradient of some scalar field. And just to make things look nicer in the end, also dimensionally, he says, oh, I write this as h bar divided by m times the gradient of some scalar function. And then this scalar function is dimensionless. Okay. And it's called phi for no particular reason, but we will see. Okay, and otherwise you do the same as before. You will demand again that the acceleration is the same as you would expect from Newton. And then it turns out you get not only information about rho, what should be the rho of this random process, but also about what should be the full drift velocity, and thereby what should be this extra phi field. So you get both a rho and a phi by this condition. And then if you put them together and you say, oh, let me just for fun look at a new complex variable that I let be square root of rho times e to the I phi, then it turns out that this psi does fulfill the time-dependent Schrödinger equation. So that's amazing, yeah? So now you not only got the time-independent, but also the time-dependent Schrödinger equation, and this is where your phase comes in. So that's amazing. The other very interesting thing about this is it makes very clear connection with Bohm. Because if you look now at the right-hand side of this equation of motion, the last term, the gradient of phi, which we now have identified as the gradient of phi, that's exactly what Bohm would tell us, even up to including the prefactor, by the way. Yeah? And then the other two terms, they are, of course, noise and diffusion. Noise, which means diffusion, and the drift term. So overall, this equation looks like starting from Bohm and adding drift and diffusion. And so this makes also a lot of sense. So Bohm itself already, I know that Bohm itself gives me, will give me consistency with quantum mechanics. So if I add on top of that some diffusion, I would create a problem because diffusion has a tendency to broaden the probability density and make it spread out over larger volumes. And then I would contradict quantum mechanics. So what I need is not only a diffusion term, but yet another drift term that has the tendency to bound this diffusion and bring back everything to where it should be. And so then this gradient of phi plus this balance of drift and diffusion, together they conspire to also give me the correct probability density. The same probability density that Bohm would do with purely the gradient of phi term. Okay, so here's a remark. As for Bohm, the physical picture is very nice for particles, but looks strange for quantum fields. I kind of agree. I mean, it's already kind of annoying that in the ground state of the hydrogen atom, the particle just sits still. This is kind of not what we expect. Also seems to contradict things from, say, relativity theory. We know that there is some motion, really, of the electron. But for quantum fields, it's even more disconcerting because Bohm would tell us that if a quantum field is in its ground state, it would just sit there frozen in a particular configuration of all the field values, and that's it. Yeah? And so I agree that this drift diffusion maybe looks better. Another question is this, I suppose you mean Nelson's thing. Is it like Bohm's picture, but with the difference that the individual realizations swap randomly? No. So in Bohm, the difference is even on the level of individual trajectories. So if this is a Bohm trajectory, this will be a Nelson trajectory. So it's not as if I have multiple Bohm trajectories and then I just, so to speak, just suddenly jump around. At least I don't see a way of how to construct it in this fashion. Very other good question. Is Nelson's approach in any way related to basically imaginary time path integrals? Okay, I would want to say probably yes. That's a very good question. It has the same ingredients. It also has to produce the right density if I have a particle with a normal kinetic energy, then I expect some such term that looks like a random walk. So I'm pretty certain that you are right, at least in the time-independent case. But I would have to check, but it looks very right to me. Maybe I should know, but I will check it. But you understand that the starting point here is conceptually very different. In imaginary time path integrals, we start from the Schrödinger equation and then we follow Feynman in reformulating them, and we know that this must be consistent with the Schrödinger equation. Also here, if you tell me, oh, I wanted a drift diffusion process that would give me the right density for the Schrödinger equation, then it would also be rather easy. But here the starting point was very different, right? We started from drift diffusion processes. We said, oh, let me postulate that the acceleration should equal the force divided by m, and let me just see what happens. And then we arrive at the Schrödinger equation. So it's the other way around, and this is what impresses me. Okay, good. Okay, so this was Nelson's theory. Is there still a question? I should say that Mr. Nelson, when he derived this, in principle, Bell was already around, but it was not very well known. And then apparently in the 80s, he met with Mr. Bell, and Bell explained to him that his theory is non-local. So Mr. Nelson had not understood this so far. And then Nelson rejected his own theory because he didn't like having a non-local theory. But we now know it must be non-local if it is consistent with quantum mechanics. Okay, very well. So in the last 10 minutes of today, I still want to start another commentary on Bohm and Nelson, which has to do something with relativity, and it's also very interesting. Okay. So what do we call this chapter? Just a little. Yeah, so let's look at any hidden variable theory that is consistent with quantum mechanics, of course. And let's ask the important question, can they be Lorentz-invariant? So to make it really more precise is, we want to ask the following. We already know that if I look at Bohm or Nelson and look at the probability density at a particular fixed time, then it completely matches the density that quantum mechanics predicts, even for multiple particles. But now, if you are in relativity and I say something like at a particular fixed time for many particles that are at different positions, that should ring a bell, yeah? It's dangerous. So what we want to know is, can we construct a hidden variable theory? I will now abbreviate it. That reproduces the quantum mechanical probabilities in all reference frames. So regardless of how fast the observer is moving, and therefore also regardless of how exactly simultaneous time is defined. So just to make the picture really, really clear, is here's my space-time plot. Here I say I the particle trajectory 1, and then simultaneously the trajectory of particle 2 at another point. And what I want to check is, I could now take different space-like hypersurfaces. Yeah, so for example, I could say, oh, let me just take a fixed time t, so that's a horizontal line here. Or I could say, no, I'm moving with a certain velocity, so my space-like hypersurface is actually tilted a little bit, like this. Yeah? And the question is, can we make it such that the probability of finding the particles at different spots here, simultaneous in these different frames of reference, can we reproduce quantum mechanical probabilities in all of these reference frames, regardless which one I pick? So this is not guaranteed so far. Anything we discussed was always there is a fixed absolute global time. And if I then talk about matching quantum mechanics, I always talk about measurements where I measure all the particles simultaneously at this particular time, and then I'm fine. So it turns out that for a single particle, this actually works. There's a Dirac equation extension of Bohm. But the question is beyond that, if I have more than a single particle. Okay. And so, well, the answer will be no, it doesn't work. And that's quite an important answer, I think. It's not very well known. And in order to understand this answer, we have to look at something like a Bell experiment, but with a state which is cleverly chosen. It's not our typical singlet state, but a little bit different. And so this, the original wave function is due to a person called Hardy. And the modification I'm showing here is a modification invented a few years later by some other people. Okay, so consider a wave function, which I call Hardy's wave function. It's again 2 spin 1/2 particles, but the wave function looks a little bit funny. So it's up and down. So particle A and particle B. So this is how it starts. It almost looks like I want to write down a singlet state, but then it's a very funny second piece. So to write the second piece, I don't even stay in the Z basis. So this is actually, I hope I get it right. Okay, up to a sign at least, up minus down. So it's the spin X eigenstate for a negative eigenvalue. Okay, so this is at least this is a valid wave function, and one can check that it's normalized and so on. It's also obviously an entangled state, even though it's not maximally entangled, but still it's an entangled state. So this is all good and fine. And then I can rewrite this just by inserting this expression here. I skip a few lines and I tell you what is the result. It's 1 over square root of 12. Okay, don't ask me, no deep meaning of 12. And I write it in the X spaces. And it will have really all 4, we'll have all kinds of different components. So this is the X spaces. But I can also write it in a slightly different fashion, which is, let me see. For example, in the Z basis, I could say it's up, down, minus, up, plus, down, up. And so you can rewrite it in many different bases. Okay. And why do we do this? Because we can now conclude certain things. For example, if I measure A in the X spaces and I find +1, then I immediately know what will happen if I measure B in the Z basis. So this comes out from one of these versions of the wave function. It turns out that BZ will then be -1. So in the Z basis, it will be pointing down. Maybe I forgot to write down this particular state. Okay, I apologize, but you can check this. So the overlap of this overall wave function with the opposite possibilities, so where A is indeed pointing in the positive direction, but B would be pointing in the up direction, this overlap of the other possibility is actually 0. Okay, so this is one of the consequences one derives from this kind of wave function. And then I can switch the roles. I can say Bx equals +1. That means blah, 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 blah. Az equals -1. I will also find that Az equals -1 and Bz equals -1. This actually never happens. So I think this should be, yeah, this is visible from this third version. Here there are exactly 3 contributions, up, down, up, down, up, but it's never down, down. So this never happens. And then finally, final consideration, if I look at the probability to get both Ax is +1 and at a simultaneous measurement of Bx also +1, this probability I can actually read off from this version of the equations, and it's the first term, and it's 1/12. Okay, so it does happen, not always, but sometimes. And I think maybe it's enough for today, but what we will do next time is we will set up a very clever kind of experiment that combines ideas both from Bell and from the quantum eraser and works on this wave function. And we will then look at different hypersurfaces. And by using what we just saw here, we will find that there is no hidden variable theory that is able to provide consistent results for all these different hypersurfaces. So neither Bohm nor Nelson nor anything else that you could possibly construct. And that's quite powerful. Okay, and then we will still talk about possible extensions to quantum mechanics where we really modify quantum mechanics, and that will be next time. Okay, is there a question at the moment about this? Or maybe about any of the stuff we looked at. Well, if not, let me just remind you, this Wednesday at 6, there's the tutorial. And I post the link on the website. So if there's no further question, then see you next time, which is actually the last lecture in this series. See you and thank you.